Welcome everyone to this video series on linear algebra for business analytics. My name is Teja, and in this video we're going to look at an important, precursor to understanding, for example, principal component analysis eventually, and this and also what is called eigen decomposition. And so today we're going to look at the basic building block for that, which and the concept is called change of basis. Okay, so whenever I describe a vector, for example, I say, oh, I have a vector which is 10, 3, I'm actually implicitly telling you what is called a coordinate system. Right? I didn't have to tell you that the 10, 3 actually corresponds to an x-axis where there's 10 units on this side and maybe y-axis with 3 units on this side, right? So I implicitly assume that this x-axis which is going towards the east has this unit basis vector, and the y-axis has this unit basis vector e2, and 3 units of the second vector and 10 units of the first vector is this representation when I write 10, 3. But I could also have said, okay, I have this vector 10, when I mean that, when I said that, maybe I meant some other coordinate vector, right? It's, let's say there's a space vectors, but my basis vectors happen to be this vector and this vector, okay? So this is my basis, which means that in my point of view, somehow it's tilted. This is my E1 vector, and this is my E2 vector, okay? So in this basis, okay, under this coordinate system, I have 10 units to the right here, and 3 units to the top here, so which is so this is the vector I am describing, okay. Whereas here I'm describing this vector, right? So think of these 2 points being absolutely, in the absolute sense, these 2 points are different. So for example, this was a different plot. So let's say I this was the origin, right? 0, 0. Let me map this, let me synchronize these 2 plots as a 0, 0 is aligned. Then this point over here, let me put it as a cross, would be somewhere over there, right? So this point is different from this point just because the basis changed, right? So in my language, maybe I meant 10, 3 in this basis, which means the cross point. Whereas in your language, you meant 10, 3 to be this point because in your language, the basis vector is maybe the standard basis vector, which is 1, 0, and this one being 0, 1. Okay, so I'm using the word basis again and again just to recall. Basis is just a number of is the set of linearly independent vectors that span the space. The space is the same. For example, this cross point and the dot point are in the same space, except that I'm using E1 and E2 to span the space in one version. And okay, maybe I should not use E1 and E2 here. Maybe let's call it and B1 and B2 to span the space. Okay, so so this would be called a different coordinate system, and this would be called a different coordinate system because they have different bases. Okay, which means that, so I said, with the same vector representation, I have 2 different points. If I have the same point, then I have 2 different vector representations, right? So for example, so let me draw an equivalent picture for that and think of a different point. So let's say my original basis is going to be this E1 and E2, right? E2. My second basis is going to be something tilted. So let's say something like this, B1 and B2. And this nomenclature is, I just chose E1 and E2 to be the standard basis and B1 and B2 to be some other basis, okay? And they're not even like this. For example, oops, doesn't look like straight. That doesn't look straight. Okay. So B2 could be something like this, okay? And E2 is still like this, okay? So maybe it's the same dot. We know that this dot maybe is 10 comma 3 in this original basis, but this dot is going to be something else, right? Originally it was not this one, sorry. So this is 10 comma 3, right? This point in the first basis, first coordinate system. The second coordinate system, this particular dot may be something else. It's you can imagine that this is like some multiple times b1 and some negative multiple of b2, right? So that maybe that number is, for example, here it looks like it's maybe 9 and minus 2, for example, in this basis, in the second set of bases, okay? So this is the difference. This is what I mean by change of basis. So there are two different bases, two different coordinate systems for the same unique absolute point in space. Okay, that's for the same point in space. Or if you have the same vector representation, unless you tell me the basis, they could mean different points in the space, right? This x and this point and this dot, for example. Okay, so that is the notion of change of basis. That's the notion of different bases. And now we're going to discuss how to go from one representation to the other. Okay, and before I jump into that, why are we looking at changing bases? It's going to be useful to, for example, think of visualizing data. For example, think of very quick example. Think of a bunch of as I said, feature vectors are just vectors, and therefore they are just points. Maybe there's a bunch of points which are like right next to each other like this. Okay, then maybe instead of talking about two different, each point is, because it's a 2D space, each point is represented using two numbers, right? Instead of doing that, maybe I change the basis to maybe something with this as one of the basis vectors, and maybe something else. I mean, in this case, it doesn't matter what this is. So let's pick a basis vector. Maybe in this basis, you see that each of these data points need to be represented using only a single number, because on the second basis there's really no there's no need for a number, because all these points are just seem like they are on the same span. They are on the span of a single new basis vector. Okay, in this case, this basis vector. So there is some value in changing basis to understand data better, and we'll see that more precisely when we look at the motivation for principal component analysis, or this eigen decomposition. Okay, but anyway, let's get back here. So how do we change from one basis to the other? That's the question that we want to tackle now. So let's say so first of all, when I wrote, when I put the two basis vectors and two sets of basis vectors in the same, next to each other. So this was E1 and this was E2, and I said, okay, let's pick B1 here and maybe some other, B2 over here. When I did that, you can easily see that I'm thinking of a transformation. Let's say some transformation where I can think of transforming E1 to B1. So that can be done by taking B1 as the first column of the transformation and B2 as the second column of the transformation, right? This we saw in just the thinking about linear transformations. They just think, if you just think of how the basis vectors, in this case the standard vectors, get transformed, then that kind of captures the transformation for any other data point. Okay, so so this B1 and B2. So when I wrote B1 and B2, just think of them as actually. So let's say, what is B1 in the first coordinate system, in the E1 and E2 coordinate system? Maybe B1 looks like 1, 1 to me. Okay, B1 looks like 1, 1 to me. So write 1, 1. So this is a representation of B1, which is a vector in the first coordinate system, right? Similarly, B2 looks like it's somewhere, it's like -3 and maybe 0.5. So maybe -3 and 0.5. So this is a representation of B2, which is a basis in a second coordinate system, but its representation in the first coordinate system is this. So this is a transformation which can transform my current basis to a new basis, but this basis is only represented in my language in the sense of in the first coordinate system. So let me just write the first system and the second system. Okay, the first system, the basis vectors are e1 and e2. In the second system, the basis vectors are b1 and b2, but when they are represented in the second system, they are essentially going to be just 0, 1 and 1, 0. For example, e1 and e2 are just 1, 0 and 0, 1, right? In the second system, these b1 corresponds to this guy and b2 corresponds to this guy. So their representation in the second system is just this, okay? Whereas their representation in the first system is going to be, for example, these numbers, okay? And this is called the change of basis matrix. Basis matrix, okay? So it's just a matrix of columns with columns, where columns are just the representation of the new basis vectors in terms of the first system itself, right? In terms of the first system itself, because in the second system, these basis vectors are just going to be represented as the standard basis vectors, okay? In that system, okay? We would imagine that those are the vectors. So now, what can we do with this? So this matrix, let me call this matrix so let's say there's a vector in the second system. Let's call that vector a and b, okay? So if there's a vector in the second system, and I want to ask, okay, what is the vector in the first system? Okay, what is that vector in the first system? In the second system, a and b means it's, a and b means in the second system, for example, in this case, it would be some units a on this side and some units b on this side, right? But in the first system, what is the equivalent? Maybe a and b in the second system corresponds to some point here, okay? In the first system, what is that equivalent point? In the second system, it would be a and b, right? In the first system, I'm suggesting that that point is nothing but equal to this change of basis matrix A times A and B, okay? Because you remember the columns of A are already, it's like saying I've already transformed the basis vectors of the second system into the first system, which were the columns of A. And therefore, if I scale them appropriately, which is what matrix vector multiplication is, I'll scale the first column with A and scale the second column with B, and then add them together. That's what this is, right? So it's like A times 1, 1, okay? A times 1, 1 plus B times -3 and 0.5, right? So the vector in the second system is a representation of a comma b in the second system has an equivalent representation in the first system, which is given by the change of basis matrix times the vector in the second system. So I can go from the second system representation to the first system representation by multiplying with this vector a, okay? And similarly, how do I go back how do I go from the first system's representation? In the first system, let's say there's a representation x comma y, okay, in the first system. By the same token, we saw the inverse of a matrix, right? So by the same token, we can think of a inverse acting on xy to give me a representation in the second system, right? So this is a change of basis from the which can translate from what I thought, what I think the vector is in terms of my standard basis vectors to what would be the vectors coefficients, right? These two coefficients in terms of b1 and b2 vectors in the second system. Okay, so this is what is called. So these are essentially the transformation matrices which can change the basis. Okay, so I'll end this with a point about transforming the two different coordinate systems. So the main point is that the transformation, a linear transformation such as A, such as in one system, let's say in the first system. Okay, actually, no, let me not use A. A transformation such as C. Okay, C, let's say, is a transformation transformation in one system, let's say in the first system, is not same as the same transformation, is not the same as the transformation in the second system. Okay, and what do I mean by that? So let's say if you want to apply transformation which is equivalent of C in the second system. So I want to somehow apply C in the second coordinate system. Then what should I do? What I should do is the following, which means that I want to apply this transformation to a vector which is represented in the second system. So let's say AB is a vector which is represented in the second system. It's the same. I think I was using AB notation before. So AB is a vector. Then what I should do is I should transform it into the first system. Let's say the transformation is XY. Okay, this transformation, we know how to do it. We have the change of basis matrix A to go from the representation in second system to representation in first system. Then the first system, we know what the transformation is. It's just the C. Okay, C is the transformation first system. Then we get some vector, maybe U and V, right? That what we'll do is we'll inverse transform it using the the final transformation C and D, let's say. So this is how you would transform AB to another vector CD. So this is the input vector, this is the output vector, this is the output vector. And to get from input vector to output vector, using a transformation which was specified in the first system, you have to go to the first system through A. Remember, this was just a collection of system in terms of the first system. Go to the first system, apply the transformation C, and then the inverse transformation to get back to the original system. Okay, so and you can see that, and so this, if you think in terms of matrix multiplication, this is nothing but A inverse times C times A of a representation in the second system. So whatever is the representation in the second system, if you do these operations, you'll get a vector in the second system whose transformation would be equivalent to transforming their equivalent representations in the original system with a C, right? In the first system, a transformation with respect to C is the same as a transformation with respect to A inverse CA in the second system. Okay, thank you for watching.